the things I used to do. So we'll see if we can get better this year. I'm almost about ready to pay my own money to use Screencastify out of my pocket. But anyway, here we go. We're going to start these notes and go fast because they're not bad. I think these are things that you should remember for sure. And I don't know why this seems new this year. I thought I was able to hide this. I'm a little afraid to do anything other than put this all the way down there. Okay, so what is a function is what we're starting off with. So the basic terms, a lot of vocab. I had someone in AV go to me after one of our lessons Tuesday. The next day, I didn't understand a word of your lesson. And I go, ma'am, it's just vocab. There's not understanding. There's learn the vocab. I mean, there's nothing. It's like a dog has four legs and barks, and it comes in a room. It comes in and barks, and you go, cat. No, I'm sorry, you're wrong. That's a dog. This is a definition. You either know it or you don't. I don't know what to tell you. And there's a lot of things in math like that that you need to lock in. All right. And this is going to be very vocab heavy early because that's what the AP exam is. I'm going to tell you right now. I actually asked our AP coordinator this very question after 2 years ago, about a month into it. I go, does AP take it a subject? All right. And really complicate it with the wording of the questions. Even though it's similar math, the student has to figure out what the heck they're asking. And she goes, exactly. And I'm not kidding. That's what it is. It's this very complicated worded questions, and we're going to have to work a lot on that. And that will come when we actually go into the AP program, or the AP class, and look at the questions and see how they're worded. And you're going to see that's what you're going to have to do. You're going to figure out how to disseminate, which is actually figure out what they're asking. The math behind it is probably not that bad. You just got to figure out what it is. All right. And there's going to be a lot of that. Just watch. All right. Again, take a deep breath. For BC, the numbers were extraordinary. I think I had only one person get less than a 3. And I told you they got a 1. And I know what they did. They probably turned in all 4 blank written problems. And they probably picked A in the multiple choice because they just didn't have the right attitude. I'm sorry. I'm serious. So we'll make it work, I hope. And hopefully we have a similar situation of success and I don't have one of those people that has a bad attitude. All right, so here's the function definition. I've always hated this definition because in high school, I didn't understand it. I didn't know truly what it meant. So I always add this caveat in a simpler definition. You know what a function is? It is a relation that quite simply has no repeating x's. That's it. That's what this sentence ultimately says down here. Now, I do like input. Say it. Oh, you guys are not trained yet. Input, say it. Input, no, I've said this in here. When I say input, what's the other thing? Output. So input, say it. Okay, I'm going to say this a billion times in here. As a matter of fact, everything that we graph this year, going to be a series of inputs, outputs, which are called coordinates. Nice. Ninja over here. Math ninja. All right, coordinates. And then you graph the coordinates, like maybe 5, 6, 7, 8 of them. And then you connect them. And that's a picture. But the picture has more than those 5 coordinates. There's an infinite amount of coordinates. We just don't want to do them all. I mean, we don't have all day to do a whole bunch of inputs and outputs. So for something to be truly a function, there are no repeating x's. Now, I'm going to throw some stuff at you here. Is this a function, which is a classic cubic? You know, right there. Is that a function? And the answer is yes, because what does it pass? What is this test called, everyone? Vertical line test. Why? That proves this is a function. That proves every x is unique. There are no repeats. Here, I'm going to draw a non-function, which is a picture of a circle, which you had a lot last year. This is not a function because when I draw this vertical line, that's a 2 time and no good x value. That x value is going out with this y one night and then this y another night. No good. All right, got it? All right, and that's why that's not a function. It fails the vertical line test. But then I do want you to know this. Are there repeating y's in this graph? Oh, definitely. Still a function. Know this in the future. It's just considered not a one-to-one function. And hopefully that terminology was used with you last year. You don't necessarily need to know that right now, but in the future you will. Oh, shoot, I didn't even see that. I had no repeating X's already written down there. So now I wrote it twice. Okay, some other words that you should know. Input, say it. All right, good, you're better. And then input's domain, which is usually X, which is the independent variable. Output is range, the dependent variable. Okay, and then you could read this this thing right here. Throw a football and measure the height. We could use variables. H is the height of the football, and T is the number of seconds. So here we go. I'm going to give you a functional statement. The height of the ball, gotta start over. The height of the ball, when I'm looking at that ball, like I'm over here and someone throws it and I see it fly through the air. How high the ball is depends upon the time that I look at it. Did you hear that? So the height of the ball depends upon the time. Time is independent. I can look at it at 1, 2, 3, 4, 5 seconds, but the height is the dependent variable. It depends when I look at it how high the ball is. Does that make sense? Okay, so input, output, there's a sentence of a function. All right, so another one here is, ooh, I just swam last night. Oh my gosh, I have a pool. I like this question. And actually, I do have a pool that's an oval. It's very long. It's like 10 by 20. So, and I had a chance to get a bigger pool. So the longer the pool is, anyone? The blank amount of water. What's the word I'm looking for? So if I get a longer pool, there is more water in the pool. So the amount of water in the pool depends upon the length of it, and actually the width. But let's say the width is static, so the width doesn't change. I think that was true. I could have had a 10 by 30 or a 10 by 20. Maybe. I may be wrong on that, but nobody cares. Anyway, stop talking about your pool, Mr. Samulus. All right, intervals of increase and decrease. I just threw a upside down parabola there. We read graphs left to right. Okay, so hopefully you already know this. So I threw an upside down parabola and then I highlighted. And then I'll grab my blue for the highlighting of the the next part of the graph here in the sentence. So this component from here to here is increasing, and then this component from here is decreasing. So I got to grab that and then hit that right there. I don't think I mentioned this to you. It might be a good idea to grab highlighters and have them for notes. It's nice. I'm going to have a lot of printed notes. So if you have highlighters, you can hit things exactly the way I am. Okay. We like these kind of questions because actually so does the AP. Drawing questions from a situation just listed up here. And then what these are intervals. So I want you to understand that they are labeling, these are the X's. This is the X's that I have to look at on the graph. So these are the inputs. So from these inputs, I want outputs that are doing this. So that is increasing on the interval this. So I need a graph that shows increasing behavior. The increasing is describing the Y's. So I want you to understand that as well. These words are describing what the Y's are doing when I input these X's. So from negative infinity, negative infinity. I'm in the room here pointing to my left. Forever that way is where negative infinity is. You better understand that. Forever right is where you have positive infinity. So from negative infinity to -2 is this set of x-axes. You can go anywhere you want. All you need to do is I got to make sure I label this correctly, make a graph that continually increases up to this point, and then I might do a stop right there. I tried to make that more curved. It doesn't have to. You can do whatever you want, but make sure it's increasing. Make sure when I read this left to right, you follow what's being said in this little set of parameters. Constant on the interval. I guess blue does not really stick out compared to green. On the interval -2 to 4. So, I stopped short. Stop short. That's my move. Sorry, no one knows Seinfeld anymore. All right. Does anyone know that reference? Anyone a Seinfeld fan? Are you? Did you move your hand? You're a Seinfeld fan? The donut winner? Nice. Are you like sad about your prize, or is it okay? Okay, all right. Uh, she got a scented donut, but it doesn't have the scent anymore. I guess it's too old. One, two, three, four. Oh, I'm so super shaky right there. All right, constant means it doesn't rise or fall. It's a what kind of line? Don't say purple. Don't say straight. Starts with an H. Horizontal. It's a horizontal line. All right, and then the last part, I probably should speed this up. 4 to infinity, it's decreasing. I don't know. Maybe I'll just go red. Oh yeah, red. We could just do like a let's try to be fancy and do like a curve. You don't have to. Just make sure it's doing what we asked there. All right. So increasing, constant, decreasing, and then marks on the x-axis. It looks like I'm off again. This is a really small grid, but do the best you can. Okay, and then I'm going to go back up to this, and we're going to fill in these limits. All right, and hopefully you remember this last year. I know you did this last year. So here's what an end behavior limit statement is, and then these are already marked here. What vertical direction is y going in as you move in the direction of the arrow? So y values increase. When y values increase, you're approaching infinity. When y values decrease down, you're going to negative infinity. All right, so I have nothing to fill in here. I'm going to go back up here and remind you what this means then. So my first limit, as x goes to, let's pick a color, green, negative infinity. That means as you input x is going to the left, where does y go? What's the answer to that? Where's that y going? Negative infinity. So as x goes to negative infinity, so does y. So this is what x is doing. This is what y is doing. Remember that, right? That was definitely something that you had last year, no matter what you were in. Definitely, yeah. So I know we have people that were in different classes sometimes, so it's definitely a math language. Now, as x goes to positive infinity, input, say it. Good. Some people, you're losing it here. So as I plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20, 50, 90, 100, hike. As I'm plugging all these in, where are these y's going? Again, it's another negative infinity. All right. So remember how to fill in those limits. That's all I got to say about that. Okay, so let's go on to the next page. I don't feel like graphing lines. I just did one of these two. So I did this one. Recall, I'm not teaching this. Right now I'm in AB and we're doing linear stuff, and we did a quiz is. My second hour got a 52% on a slope and a y equals mx plus b quiz is. I want to hit my head up against a wall. That's grade school stuff, man. Okay, so y equals, or sorry, 0 comma 3 is the y-intercept, and then negative 1/2. Rise, fall, sorry, fall 1, run 2. Fall 1, run 2. Know how to graph a line. Now, I will tell you this. If it said just graph this, then the smartest thing to do would be just find the intercepts. So here's how I do it. I do this with my brain or my hand. Pretend this marker or this pen is my hand, and I cover this up. Why? What did I just plug in for x if this gets destroyed? 0. So I plug in 0 for x. What do I get for y? 3, 2, 1, south? 4. So 0 for x, 4 for y is the y-intercept. Okay, so I plugged in 0 for x and I got 4 for y. This is Mickey Mouse 101 basic math stuff. All right, and then next, if I plug in 0 for y, that means 0 for y. What do I get for x? 3, 2, 1, go. It's simple. Simple solves. 3, 4, 5. Input, say it. That's it. This is how you graph. Now, a line we know is straight. And it always drives me nuts when people say it's a straight line. That's a redundancy. That's like, I don't know if I'm allowed to say this these days, but that's like saying, hey, that's a female girl and that's a male boy. Right? Get it? Straight line. Don't call a line straight. Lines are straight by definition. All right? When people say that, even mathematicians, I cringe. Did I go through with you guys? I couldn't care less. Did I draw that on the board? Okay, never mind. Sorry. We'll get to that later. It's one of my pet peeves as well, just like someone saying a straight line. Okay, which of these graphs are increasing? Well, I didn't do the first one, but this would be increasing because that has a positive slope. Pretty simple. All right, which graphs are decreasing? That's B and C. Describe the end behavior using limits. I just described this one. So go ahead and throw that in there. As x goes to negative infinity, y goes to infinity. As x goes to, did I do that right? Oh yeah, no, it's right here. It's hiding negative infinity. Sorry, a little sloppy math there. So x goes to positive infinity, y goes to negative infinity. So we'll just do one of those limits. Okay? So these two, B and C, are decreasing. If I would have graphed A, it would have been increasing. All right? And then actually, if I did the limits on A, those limits would switch. Negative infinity would be negative infinity. Positive infinity would be positive. We're not going to do this one. You're gone. If you wanted to look at the key online and read it yourself, go for it. We're just not too concerned with this right now. All right, and then here we go. We can look at this one real fast. Where are we at? 8:05. Is that what that says, right? Oh, no. Okay, wait. What did I say? 18? 18? Okay, so we got, 9 minutes. Okay, so Easton walks from his house, good for him, to the bank and then to the grocery store before returning home. Don't you love word problems? I don't care about Easton. Anyway, graph shows his distance from home, d of t. So his distance from his home depends upon the minutes that you look at it, all right, during his little walk. How long does the trip take total? What does it look like, guys? 3, 2, 1, go. It looks like it is right in half. It's cut into 4 units between 40 and 50, and you're right in the middle there, so it's 75 minutes. So just the ability to read a graph, read the question, get the concept behind it, and then understand the x-axis represents minutes, right? And then he's back home. So his distance, so he's back home here because his distance is 0. So he starts at home, his distance away from home is 0. Then he ends back at home, his distance that he is from home is 0. So he's back home, right? Understanding that. How many minutes is Easton at the grocery store? Well, he walks to the bank, and then what does this horizontal line mean? He's sitting at the bank. He's doing his little stuff. And then he walks to the grocery store, and then there he's at the grocery store. What's he doing right now in this component? Shopping. Nice, good. I like it. So how long is he there? That looks like 40 to 55. So how many minutes is that? 15. So really the point of this one is, can you read and understand the graphical situation in context of reality, all right, of what this is emulating? At which time is D decreasing? Which interval? What does this mean in context of the problem? Increasing, constant, increasing, constant. It's this one. What does this mean he's doing, everyone? 3, 2, 1, go. Walking back home. So under what interval is that? So it looked like we were at, is that 55 we did that? So it's the interval. This is how you do this. 55, comma, to 75. It's over that. So from the 55th minute to the 75th minute, which means he was walking for 20 minutes from the grocery store back home. How long did Easton take to walk from the bank to the grocery store? Bank to the grocery store is 30 to 40, so it's 10 minutes. Got it? All right, then we got to go on to here and make sure we get this done. All right, and then you're definitely going to break this down. Actually, I'm going to leave my answers here for the end because we are going to run short on time, and I'll just explain it. And I'll explain the 2 different ways that we have to write answers, okay? But a 0, the graph intersects the x-axis when the y value is 0. A y-intercept is when the x value is 0. Guys, we just did that. We did that when we graphed this line right here using intercepts. Linear is easy. You'll find zeros of every single thing that we're going to mention zeros all year long. And then look for y-intercepts as well. And then I don't know if you did this last year. Did you remember the word concavity? Just shake your head, yes or no. Concave. That's weird. I don't know if I taught math 2 honors 2 years ago. I don't remember. Yeah, maybe I did. Maybe we did talk about it 2 years ago when I was still, or 3 now, I guess. All right, but it's bowls. It's basically bowls, and I'll talk about that on this next question here. I'll break it down with some highlighting. Maybe I'll erase the highlighting, but I'm going to leave my answers here. And then a point of inflection is where concavity changes. Best way to do that is to actually look at this question right here. You know what? I'm going to leave my highlighting. The highlighting that I have here is showing concavity. These are the different bowls in each part of the graph. So let's jump to this. Do they have? Yes. G. Let's go to G first, and then we can break this down. The points of inflection are located at, these are all x-axis values. G, H, I, J, K, L, and M. Those are x values. Input, say it. Those are the inputs. What are we getting at the outputs? Well, I and K, those outputs represent where the bowls change. So those are called points of inflection. All right? So that's where the concavity is different. All right, now let's go back up to here. Now we can look at A. When is the graph concave up? Okay, so it's concave up. Follow this blue here. When I input these x's, all of these, okay? That's where I get the yellow outputs that I have colored on the left. So what are those inputs? That's when x is less than I. That's writing it as an inequality. Interval notation, that's when you plug in negative infinity up to I. Got it? So there's two ways of doing this answer. In your homework, pick one. I will tell you, you got to be ready to understand both ways. The AP exam has 40 multiple choice questions, and they toggle back and forth between inequality notation and interval notation. And there's no rhyme or reason for it. They just go back and forth. You got to be ready for both. Do you understand? Okay? All right. I got a few people that shook their head and some ignored me. And then x is greater than k, because when I plug these in forever, those create these outputs, which are the concave up outputs. So that's this or k to infinity. K greater than x, I'm sorry, x greater than k. So what is x? Any number right around where k is. So any x that's greater than k creates those outputs. That's k to infinity in interval notation. All right, and then the blue part is between I and k. Some students really have a problem with that. Look at how shaky my writing is from last year. Anyway, I is less than x, which is less than k. That means any x value in between I and k would work. And you know what this is? This is just a semicolon. So don't think this is some sort of notation. I was just separating the two different ways of writing this answer. So maybe I could just put like a big solid, these are different answers. Here's inequality notation. Here's interval notation. Now, this is one thing I don't like about interval notation. That's also, doesn't that look like a coordinate? I comma k. It's not a coordinate. It's saying every x between I and k creates this behavior. Right? You got to be able to know the difference. All right, for sure. All right, and then, all right, perfect. About ready to get done. No, my timer went off. Zeros, come on. That's where it crosses the x-axis. That's G and M. Or what I like to say sometimes is that's G comma 0 and M comma 0. All right, and then the y-intercept of the function is 0 comma A, because it says that output is A when I throw 0 in for x. That's function notation. All right, I already showed you points of inflection, and then talk about the end behavior of this graph. Sorry, I don't know what this is. Let me erase this and then do the limit statement. So, and then we'll end it. So get your Chromebook out as you're getting this last set of notes in. But as x goes to negative infinity, what's the answer, guys? 3, 2, 1, go. Is it positive or negative infinity? Positive. And then what is it for the next one? Positive. It's positive, positive. Okay, so not a bad start. It's vocab. This is exactly the notes I did Tuesday with the ABers. Someone said, I don't understand any of this. I go, all I did is go over definitions. All right, so you're going to need to work on that. Okay, we'll end the video and see how long it takes to compose.